Okay, so just a few other further points from last time. So what was the point? I gave an alternative definition of the Witt vectors. Probably many of you have seen the usual traditional definition, but I'm not actually assuming you have. Anyway, there is a traditional definition, and the one I gave was an alternative. And I think the key point is that there's sort of a change in emphasis, which is, so now the Witt vector functor becomes a universal way of inflating, if you like, a given ring A such that it has a Frobenius lift. Yeah, so that kind of comes along with a few, there are a few consequences of that. So one is that there's kind of no mention really of A being in characteristic P, and in fact, in some sense, the theory is really born in characteristic 0. But that's even true of the traditional Witt vectors. If I challenge you to kind of write out a development of the theory of Witt vectors where you never mention, where you somehow can construct Witt vectors for arbitrary rings in characteristic P, but not for rings in characteristic 0. And the way basically, the only way to prove anything about Witt vectors of rings in characteristic P is to lift those rings to characteristic 0 and prove theorems about the Witt vectors of them, and then pass back down to characteristic P. This is sort of the ghost, if you know something about Witt vectors, it's this ghost principle, where things are kind of verified in characteristic 0 in the ghost components, and then you pass back down to characteristic P. So let's see, a few other points. So this approach, so the pluses are that no formulas are needed. The approach I gave kind of used some formulas, but they're really, I kind of only use them superficially. It'd be easy to eliminate them. Unlike the traditional approach, which really kind of relies on formulas. And you even have to prove some lemmas about those formulas, some congruences to even define the Witt vectors traditionally. So not only did we not have any formulas and really rely on any formulas, we didn't even have to prove anything. It was all kind of formal. What else did I want to say? But it does have a few drawbacks. It's not superior in every sense to the traditional development, but I'll mention that after I talk about the traditional approach. Yeah, okay, so another quick comment, why, if you're interested in the case where A is a perfect FP algebra, then I would say there's not really much to be, which is somehow in the perfectoid theory, it's for the most part what people are interested in. Then I would say that this approach doesn't really offer so much beyond the traditional approach. But in fact, the traditional approach is also quite heavy-handed because there are kind of many ad hoc ways of constructing this in this case. So often people do it by deformation theory, and in Serre's book, Corps Loco, I think he just looks at perfect fields, but I think the same construction would work for any FP algebra. So it's just kind of some universal, canonical, formal way of thickening it up to characteristic 0. So in some sense, the main point of the traditional definition or of the approach I'm talking about is to handle rings which are more general than perfect FP algebras. You might ask why? Why do we care about them? So one example, which I won't really talk about, is de Rham-Witt. So why? The de Rham-Witt complex, you want to take the Witt vectors, in the degree 0 of the de Rham-Witt complex is just the ring of Witt vectors of your algebra, which is the coordinate ring of a variety. So it will basically never be a perfect FP algebra. I won't say anything more about this, most likely, in these talks, but another thing I will say something quickly about is moduli. So say R, so the point is what happens when you have a delta structure on a moduli space? And since I don't want to talk about delta structures on non-affine schemes, we'll just assume it's affine. So X is some moduli space. Then what do we have? Well, the A points of X are, of course, in bijection with the homomorphisms from R to A. These are ring homomorphisms, of course. But R has a delta ring structure. So remember the universal property. So if you have a ring homomorphism from a delta ring to A, then it lifts uniquely to a delta ring homomorphism. Oh, I don't think I actually defined what a delta ring homomorphism is. It's just a ring homomorphism which commutes with the delta operators. So delta rings form a category. I kind of implicitly use that quite a bit, but I don't know if I ever actually said that. So then this is naturally in bijection to the delta ring homomorphisms from R to WA. And this is, of course, just a subset of the ring homomorphisms from R to WA, which is identified with the WA points of the moduli space. So composing around that way, we see we get a canonical way of thickening up A points to WA points of this moduli space. In other words, you have a theory of canonical lifts. So slogan is, if moduli space has a delta structure, if it's not affine, you have to define what that means. But the same principle, but this is still true. Then the objects it classifies have a theory of canonical lifts. Then I'll just say it has canonical lifts. In the sense of certate, I guess you might say. So for instance, the moduli of ordinary elliptic curves has the p-adic formal scheme, which is the moduli space of ordinary elliptic curves, say with some level structure, is torsion-free. It's smooth, formally smooth over ZP. So it has a Frobenius lift on it, which is modding out by the canonical subgroup. So that defines a Frobenius lift on the moduli space. Therefore, it defines a delta structure. Therefore, you have canonical lifts. So that I just told you. I just gave you the definition of a canonical lift of an elliptic curve. So in this case, if it's affine, I mean it's coordinate algebra. If it's non-affine, then one has to define this. So that would require another couple of lectures to define that. But the principle is true generally. Okay. This is the second paper I wrote with Gurney. This is the first paper. Should write his name on the board. Okay. So actually it has canonical lifts, maybe I should say, for arbitrary families. That's kind of... So if you have any family parameterized by spec A, say any family of ordinary elliptic curves, then that lifts to a family over the Witt vectors of that ring. So I think that's kind of nice. Okay, that's all I wanted to say about that. So section 4, differential operators. Okay, so just let me remind you of these analogous situations which are more familiar. So say C is just some ring, could even be non-commutative. You have a forgetful functor from C modules to Z modules. You have a left adjoint, and you have a right adjoint. And then we have the differential picture, which is differential rings, forgetful functor to all rings. We have the right adjoint, which was this what I called the differential Witt vectors, but just divided power series. And then we have a left adjoint, which I haven't told you about yet, but I think I'll denote it like this. It's kind of something that looks like a tensor product. Well, it's the free, you can just imagine what it is. It's the free differential ring generated by a ring. I'll write down the definition in just a second. Sorry? Yeah, this one's the left adjoint of this functor, and this one's the right adjoint, so they both go back. Yeah. Yeah, and then so we have delta rings, forgetful functor to rings. The right adjoint is the Witt vector functor, and the left adjoint is something which is also pretty easy to imagine, but I'll tell you what it is, and I'll denote it that way. It's some kind of generalized tensor product. But let me first just make a few points about the linear situation. So C is, of course, well, you can think of it as the free C module on one generator. And that generator is 1, which in some sense is the identity linear operator. You can also think of C as the natural. So given any C module, given any element of C and a C module, you get a function from that module to itself, which is multiplication by that element of C. And so every element of C gives that, and that's functorial. So it gives natural operations on objects of the category. So the natural one-ary operations on C modules. So in that sense, you can recover C itself from the category of C modules, I guess together with the underlying set functor, by saying C is just the natural transformations of the underlying set, the functorial natural transformations of the underlying set to itself. Okay? Sorry? C may be non-commutative here, actually. It's left modules, yeah. Though it's not, this is just really for, to put you in the right mood. And you can also think of C as the representing object for this right adjoint functor, the somme functor. Of course, I mean, as I've written down the functor, it's sort of obviously C's the representing object, but say you came up with some other construction of this right adjoint, not as a representable functor, then you could define C to be the representing object. Okay, and then of course the tensor product. Everybody knows what a tensor product is. So it has some generators of the forms C tensor n, and then a bunch of relations, as everybody knows. Okay, so now in the differential context, well, now we don't have the analog of C here, but so we have to kind of make it, and the way we're going to make it is using kind of any of these principles. So now let's define D to be the free differential ring on one generator, and the generator, I want to think of it as here the generator 1 was the identity operator for C modules, and now I want to think of it as the identity operator for differential rings. So let me just call that E. And so what is it? Well, you need to have E, and you need to have all its derivatives. So we just adjoin them formally, and let me just call D the derivative of E, and D composed circle 2. These are just formal symbols. That's D of D, and so on. If you like, we can think of E as D composed with itself 0 times. So this, okay, that's the free. It's quite easy to check that really does have the property of being freely generated as a differential ring by this element E. I will write that down. But of course, I mean, what is an element of this? It's just some polynomial expression in iterates of the nth derivative operators, which we typically call an algebraic differential operator. So that's just a word. It's just to, again, kind of make us, I don't know, it's just a useful psychological thing to tell ourselves that we want to call those differential operators. Okay, and then you can check. So if you have a differential operator, this defines, I mean, what is it? It's a polynomial expression in these. So given a differential ring R, so R It's a differential ring. Of course, it has a D operator on it by definition, but also you can compose D with itself however many times you want, so you have all of these other operators, and then you can just take any polynomial expression in them you want, because R is a ring, so any polynomial expression in its elements makes good sense, and that will give you another element of R. So this defines, this fixed operator C defines naturally a function from R to R. And in this way, D is actually naturally, it defines a natural operation on differential rings, but in fact it's in bijection to the set of all natural operations on the category of differential rings. So this is natural one area. So you have to check that, just like you had to check this equality here. Okay, and then finally, the free differential ring. Well, everybody could have guessed this himself. So what do? You start with the integers, and then you adjoin all derivatives of all elements of A, including the zeroth derivatives, in other words, A itself, and mod out by all necessary relations. So we adjoin all symbols of this form. And then we have relations like this. So there's the Leibniz rule, which I've talked about many times. And so on. You have an additivity. Obviously, you need some additivity, and you need the derivatives of 0 or 1 are the right thing, and so on. Okay, so that's the free differential ring generated by A. Okay, so now the point of all this discussion was just to warm you up for here. So, but everything is exactly the same. So now delta is the free delta ring on one generator, which again I'll call E. Think of it as the identity arithmetic differential operator. And what is it? It's just this, where delta takes, that was kind of an abuse of symbolism here, but delta takes each of these formal generators to the next one. Yes? Z bracket delta, where? Here? These exponents, this is a polynomial algebra in infinitely many variables. These exponents, think of differential operators. You can exponentiate them pointwise, or you can compose them. They're completely different things. So f prime squared is not f prime prime. Yeah, yeah, thank you. No, this is a polynomial algebra in each of these are indeterminates. Yeah, yeah. Although it wouldn't, because differential operator, because one difference between these two things is because these operators themselves are linear, you could equivalently kind of look at a basis. You only need to adjoin the derivatives of a basis, and then you could kind of alternatively represent it as some quotient of a tensor product. The tensor ring of A? D is a ring, yeah. D tensor A over Z. I don't think so. So this would Right. So again, this is a polynomial algebra and infinitely many variables. Each of these they're just different indeterminates. And the delta structure takes each one to the next one. Okay, technically you have to check why is that a delta structure, but we know this is a p-torsion-free ring, so we can just think about it in terms of Frobenius. The Frobenius will take, maybe this is the actual definition. The Frobenius map takes the nth indeterminate to its pth power plus p times the next indeterminate. That is surely that is a lift of Frobenius. The corresponding delta structure is exactly the one I wrote down. And it has a corresponding delta structure, and it's actually given by the law I wrote down. So this does in fact define a delta structure on this ring. Okay, and we think of this as the p differential operators. If you like, the arithmetic differential operators. And they act on, so this is the set of natural one-ary operations on delta rings. So any polynomial expression in any of the iterates of delta gives you a well-defined natural functorial operation on delta rings. And now we can construct our free delta ring. So in this case, the generating operators are not even additive because they have these additive Leibniz rules, unlike in this case. So here there's sort of no hope of having a tensor product description of this, but it's the same one I wrote down. You just join all formal nth derivatives of all elements of A and mod out by all the necessary relations. And yeah, so maybe I'll just write it this way. Delta n of AB, I'll just say it's the Leibniz rule in delta i's of A and delta j's of B. So this is some explicit polynomial that depends on n. And then similarly for addition. And then for 0, I think this one's probably redundant, but anyway, I'll write it down. And then for 1, the nth derivative 1 is actually, it's 0 as long as n is at least 1, but if n is 0, then it's 1. So that's the Kronecker delta now, actually, of n and 0. So it's quite easy to check that, I mean, you would have guessed this if you kind of sat down and thought about what was going on, that this really is, so any homomorphism from A into a delta ring R extends uniquely to a homomorphism from this, to a delta homomorphism from this construction to R. So it does have the appropriate freeness property. It's the left, that's what it means to be a left adjoint. Is delta circulated quotient of D? I don't think they have anything to do with each other. Why did you ask that question? Well, what would be the map? That's true, but the relations kind of have nothing to do with these are the Leibniz rules for usual differentiation in calculus. This is for these Frobenius. Remember, maybe I should remind you since, right, so for instance, delta of AB is delta of A plus delta of B minus the sum 1 on P choose I, A to the I, B to the P minus I. Which is very different from the first year Leibniz rule we teach our students in calculus. Over here. Yeah, this is, it sends the nth symbol. Sorry, maybe this is not so legible. The nth, so delta circle, that's a circle, meaning composition, right? So maybe I should have been clear about that. Delta circle n goes to itself to the pth power plus p times delta circle n plus 1. Yeah, so maybe another way, if I had written the enumerated, called the indeterminates x's, x0, x1, and so on, then phi sends xn to xn to the p plus p xn plus 1. Oh, sorry, thank you. Right, which is very far from the usual derivative of a sum rule, sorry. Thanks. I don't think so. I mean, having a Frobenius an endomorphism which reduces the Frobenius modulo p is nothing like having a derivation on a ring. You can have both and have them be compatible in a certain way. Of course, you can, if you have a free algebra, you can say where those generators go arbitrarily. So in that sense, they're kind of the same, but the relations will be completely different. Like if you have relations in your algebra, or if you change generators. A bracket the derivations. Like you so der a. Yeah, that's what this is. Yeah. Well, yeah, so if you, that's right. So I wanted to be cute and join, I mean, the first derivatives are there automatically. So I think I could have done a join d circle n of a for. Yeah, because I guess this would be an algebra generated by countably many elements over A, and this, say if A is uncountable, I think, yeah, I'm pretty sure. Yeah, okay. Okay. Yes. Yes.
So suppose we have a R only has a digit, but not that structure. Does its universal structure?
No, I mean, so if R is p-torsion free, then it does. Okay, but if it's not, then I don't think so. Yeah, circle. I say so, that's how I say it. Yeah, there is a Frobenius. Yeah, so there does exist a unique map which is Frobenius equivariant, but that's weaker than being delta equivariant.
Right, but if there's four extents, because where R.
Yeah, well, it allows for more for broader R's, but you get weaker information about the homomorphism, right? Because if it's you could have a homomorph. Anyway, it's certainly yeah. If you're only interested in the structures of Frobenius lifts rather than delta structures, so Frobenius lift structures have problems, but sometimes they're very nice. Then this certainly does have a but it's not the free. Yeah, so the free one. So there's maybe I'll say something about that in a second. That has to do with the ghost components. Okay. So now the point of sorry, I might have, yeah, I forgot to say that delta represents the functor W, the Witt vector functor. And I need to say that. I didn't say the differential analog. This is a polynomial algebra and infinitely many variables. So the functor it represents, maybe I'll say this, hom dA, a homomorphism from D to A, you just have to say where each of these independent generators goes. So it's an infinite product. Sorry. It's an infinite product, and if you recall, the power series ring, the divided power series ring, was also an infinite product. So we can naturally identify these, and therefore the W diff functor is in fact represented by D, just as this right adjoint over here, this right adjoint was represented by C. So the algebra, in this case just the ring of operators, represents the right adjoint on the category of Z modules. Here, the right adjoint is represented by the algebra of differential operators, and here, the right adjoint Witt vectors will be represented by the algebra of arithmetic differential operators. And so that's what I'm about to write down. So D. Yeah, delta is delta V, sorry. I wanted to write it as the identity operator. Where did it go? Did I write down? Ah, here it is, yeah. So we can think of this as delta circle 1, and it's the identity operator, so we can think of this as the 0th iterate of. And D. Little d or big D? Big D. Yeah, big D. As rings, they're isomorphic. But the, yeah. But in fact, the point is that their spectra are ring schemes, and the ring schemes, in other words, the functors they represent, are completely different. So the difference between them is not visible just at the ring level, it's visible at this higher level. So the point is now delta represents W, and how does that work? So explicitly, a homomorphism from delta to A, what does it do? So I call this homomorphism alpha. It just sends we have the infinitely many generators here. Each of them goes to an element of A, and we form a big vector from them. And so you just evaluate alpha at all the generators. And this is a bijection. Okay, but the point now, why am I talking about all this? The point is that, so this gives we can think of, right, so this is an infinite product. The same would be true if we chose any other family of independent generators of delta. So this is the point. So now I'm starting to get to the comparison with the traditional point of view on Witt vectors. So if C0, C1, C2, yes? Yeah, you can call it delta, yeah. Yeah, okay, yeah. Yeah. And if you like, maybe it's better to call E delta to the 0th power. Yeah, okay. Yeah, I don't know. It's a little bit like an element of a ring. Do you think you can think of that as an element of the ring, or you can think of that as an operator, C, on a C module? So it's sort of an allowable abusive notation, but I think it is. You're right. It is an abusive notation. Okay, so suppose you have another free generating set. So, right, this can happen in analysis where you have your usual basic differential operators, the nth derivatives. They generate all the differential operators, but you can take a different generating set if you want. So you could have something like this. Then the Helms from delta to A are naturally in bijection with an infinite product of copies of A, but now what we're doing is we evaluate at our other set of generators. So we can take alpha so this gives a completely different vector. Oh, thank you. Okay, good. Everybody catches me. Okay. Yeah, that's the whole point. Thank you. Right, so this gives a completely different bijection from this, which we've identified with the Witt vectors, to, it gives a completely different coordinate description of the Witt vector functor. Sorry? As rings, as rings. Yeah, one always goes to one in a ring homomorph. I'm like in the sense of scheme theory, yeah, commutative unital rings, yeah. One always goes to one, yeah. So the polynomial algebra has the free property. You just have to say where the generators go and everything else is uniquely determined. Right, but maybe I say, but the ring structure on the right-hand side so if we identify, this is identified with the Witt vectors, so we'll continue to identify that with the Witt vectors. This gives us an alternative vectorial description of the Witt vectors, but the ring structure in these terms, just like the ring structure in these terms was determined by the Leibniz rules for the iterates of delta, the ring structure in these terms is determined by the Leibniz rule for these random differential operators that we chose. So the ring structure on the right-hand side is given by the Leibniz rules for C0. So every differential operator has a Leibniz rule. You know, Xi of a sum, you just expand that out. So the Xi is some polynomial in the deltas. Where did it go? Some polynomial in the deltas. So you know in the iterates of the deltas. So you know how to compute that when applied to a sum, and it will just be some polynomial expression. So in general, this is completely different. So this is completely different than the original description we gave. And this is what Witt's, so, okay. I mean, completely different meaning it's just, it appears to be completely different, although there is this isomorphism. If you just think of these X's and the deltas as generating the same set of differential operators, and that gives you a bijection between these 2 points of view, a ring isomorphism between those two constructions. So the point now is that the traditional W is exactly this for a different set of generating operators. Which in this lecture, operators, I'll call the thetas. Theta 0, theta 1, theta 2, and so on. So these thetas we call the Witt operators. So actually, let me just say what the first few are. So theta 0 is the same thing as E, which is the same thing as the 0th iterate of delta. Theta 1 is the same as delta, or delta, the first iterate of delta. But from this point on, they disagree. So theta 2, we'll see, is delta composed with itself twice, plus, so you can think of this delta composed with itself as a second order differential operator. You can define a filtration by order, well, just the subring generated by these up to delta circle n, you call the differential operators of order at most n. And so these two will differ by an operator of order 1. And what that operator is, I'll work it out for you. Kind of, not that this really matters, but I just want to write it down so you can see it. So E is the identity operator, that's a 0th order differential operator. Delta circle 1 is a first order 1. Now we're taking its ith power, still a first order differential operator. So we take this big polynomial and then still a first order differential operator. Okay, and then actually Arnab Saha just told me that I always assumed that you couldn't write a closed form, a mostly closed form expression for these higher thetas in terms of the iterates of delta, but actually you can, and it's not that bad. Yeah, maybe we'll talk about that later. Okay, and so these we call the Witt operators, and then the alternative generating set of the iterates of delta, I like to call the Bouillon-Joyal operators. So they're just two different generating sets. Another way of thinking about it is if we think of W, the functor, W is a functor, and we can, it's represented by delta, so in terms of, if we think of a scheme as representing a functor, then we can just say that W is actually equal to spec of delta. And each of these are just the A points of infinite dimensional affine space. So each of these generating sets gives an isomorphism to infinite dimensional affine space over the integers. In other words, it gives you a coordinate system. So this depends on the generators of D that we choose. And so the point is that on this Witt vector functor, which is kind of maybe some abstractly defined right adjoint, there are many different coordinate systems. Some are good for some purposes, other ones are good for other purposes. I think the delta coordinates, the Bouillon-Joyal coordinates, are kind of better for conceptual purposes, but for certain computations, it's good to have the Witt coordinates. So, I mean, this is just familiar from geometry where you can have some object defined in some invariant way, but you want to put different coordinate systems on it for doing different things. Okay. So the next question is, what actually are these Witt differential operators? I haven't told you yet. Before I tell you about them, though, I'm going to have to tell you about the ghost components. And those are just, well, you'll see. Actually, maybe I'll leap ahead. I'll just tell you what they are, the defining equations of the Witt differential operators, and then, but it'll take some time and probably have to spill over into the next lecture to really explain everything. So phi is a differential operator. What is it? It's just the pth power of the identity plus p times delta. And I'll omit the circle 1. Right? That was kind of the motivation of the whole thing. Delta is exactly the thing which is p divided by the difference between the Frobenius lift and it's the Frobenius lift minus the pth power operator divided by p. So So that's somehow how we defined delta way back in the beginning. And then, so we can take any iterate of delta. This will still be a polynomial. You can expand out what this is as a polynomial in the iterates of delta. And you get the iterates, so the iterates of Frobenius are still arithmetic differential operators. Let me do the second one just to illustrate it. So this is phi composed with phi, and there's a smart way and a non-smart way to expand this. First, what I'll do is expand phi. I'll substitute the definition of phi in the second factor. So this is phi composed with the pth power of the identity plus p times delta. But phi is a ring homomorphism. So this can just be evaluated to phi of e to the pth power plus p times phi of delta. And phi composed with the identity operator is, well, identity operator is the identity operator. So this is just phi to the pth power plus p times phi of delta. What is phi of delta? Phi, now we finally will use the definition of phi on the right factor. That's just delta to the power p plus p times delta composed with delta. And we're almost done, but now let's just use the definition of phi one more time, and we get that this is e to the p plus p delta, all to the power p plus p delta to the p plus p squared, delta composed with itself. And this is manifestly an element of this ring. In fact, it's a differential operator of order 2. This has order 0, order 1, order 1, order 2. And you can expand that with binomial coefficients if you want. So, okay, so that's phi composed with itself. Are there any questions on this? In my experience, kind of working in an algebraic structure where you can add, multiply, and then compose elements on, like some people just aren't used to it. They're used to addition and multiplication, but having another composition operation on top of that kind of makes people's heads bend. Okay, so then the Witt polynomials are defined by the following relation, the following recursive relations. Phi composed with n. So this, the Witt differential operators are defined by finally the Witt polynomials. Yes? This equality here? So I did two things. First, the operator phi, when applied to anything, is actually is this. Then the operator phi, when applied to e, I guess I could have written that out as e to the p plus p delta of e, but that is e to the p plus p delta, and that's just phi again. But it's actually true that it's really a kind of a composition. So phi composed, phi of e is the same as phi composed with e. And e is the identity operator. So I kind of, I don't know, I'm not sure if I cheated, but okay, so this defines doing this recursively. So if you start at n equals 0, you get the identity is theta 0, which is that. And then when you go to n equals 1, you get phi is the pth power of theta 0, which is the identity. Should I write this down? So therefore phi 0 is theta 0. Check, that's because that's the identity. Phi composed with itself one time is theta 0 to the p plus p theta 1, which is e to the p plus p theta 1. So therefore, theta 1 is delta. Check. And then shall I write out n equals 2? Okay, I'll write out n equals 2. So then now for n equals 2, yeah, so we have phi composed with itself 2 times is theta. So this recursively defines the thetas. So when n equals 2, we get theta 0 to the power p squared. Theta 0 is the identity. Theta 1 is delta, so we get p delta to the power p. And then finally, we have our new operator, which we're defining is theta 2. So now we just solve for theta 2. And I actually calculated phi composed with itself already for you. So that's actually going to be pretty easy. Now, that cancels that. And we want to solve for this, so we can bring that over to this side. And we get p squared theta 2 is p squared delta composed with itself. And then let me expand that out using the binomial theorem. So we get plus sum I equals 1 to p, e to the p times p minus I times p delta to the I times p choose I. And then, oh, time's up. So then you can so you get that formula, which is the one I wrote down there. So, okay, so next time I'll explain that. So it's kind of obvious that you can always solve for the next theta is if you allow yourself p's in the denominator, because all the previous ones are known, so you just solve for the next one. The slightly non-obvious thing, and it is this statement about congruences, that actually, even if you do that, you'll actually always get integer coefficients. So we do have an I minus 2 here. It looks like you might have a denominator, but that will only give you a problem when I is 1, and then when I is 1, you get p choose I, which is divisible by p. So, so in fact, you don't have any denominators. So next time, I'll show that these operators do exist. They have integer coefficients, and they form a free generating set of the algebra of all p differential operators, and therefore provide an alternative notion of components on Witt vectors, and those are exactly the traditional Witt components. But you see now, to kind of make this work, we actually do have to prove some lemmas, whereas everything we've done up until this point, there was actually no argumentation required, really. I mean, it was all kind of manipulating tautologies. Whereas now we finally, to make this work, the traditional Witt components work, we have to prove some lemmas about p-adic congruences. Okay, thank you. Sorry, say that again? Yeah, what about it? In fact, yeah, so the way, maybe this will answer your question. The formula that comes out naturally is theta n, say theta n plus 1, is delta of theta n plus lower order terms. if you want, you could just solve. I think so it's these forms will be deltas of lower order operators. So it is kind of explicit, but it's still inductive. As far as I know, there's not a complete closed form description of that. But then you have to get into the question of what exactly you mean by closed form.
Just appears in the relations divided goes on. Just a variable that is specified differently on row. You get universal thing which specifies p vectors.
Yeah, this is similar to your question yesterday. I've never thought about that. I guess you could do it formally, but whether it would give you anything. Well, because also though you have p's, p plays two roles. It's the wonderful thing about number theory. You can have p's in the exponents and p's in coefficients, and so you see here you have both. Some p's in coefficients, but you also have p's in exponents, and that's kind of what makes Frobenius a wonderful thing. So you can, maybe even to make this, one thing you can do, a totally superficial generalization of all this, is to, you could talk about modulo pi, say you're in working over a ramified discrete valuation ring, you have a uniformizer pi, and then say you also have a residue class field extension. And then, which we'll say its cardinality is Q. Then you can completely do the same theory of Witt vectors, same everything anyone else has done for Witt vectors and everything I've done. You replace all the p's in coefficients with pi's and all the p's in exponents with q's. So maybe now you could say if you want to fix q, you could allow pi be a variable. I'm a little skeptical, but I don't know, it'd be interesting to see what happens if you do that. Yeah. Yeah.
Is this explained by that, or
yeah, I guess a little bit. Though here, I mean, let's see. D modules are a way of talking about linear differential equations, where differential rings you can. I wrote down the square of the first derivative earlier. You can talk about you talk about any polynomial expression in the derivative, so you can talk about nonlinear differential equations. But yeah, so I guess this perhaps you could say this is kind of the, I don't know, the nonlinear version of D module theory, maybe, or something like that. Yeah, I mean, this is kind of there's sort of a whole little chapter of algebra that these rings of differential operators or operators, they represent ring schemes. The Witt vectors of A, the whole point, or one of the whole points, is that it's a ring. So this infinite dimensional affine space has a non-trivial ring scheme structure on it. And so it's a group scheme, so in particular it has a Hopf algebra structure, but it also has you might call this co-addition and this co-multiplication, and this one will co-distribute over that one, and then it even has an antipode here corresponding to negation and then you can also compose them. So then it has a composition operator on top of that, which behaves well with respect to the usual operations and these co-operations, and the same is true for delta. So yeah, so purely even at the level of algebra, there's a lot of rich structure. I think that might have been a little different than what you had in mind, but yeah, there is a whole world of rich structure.